So in the last class, we continued with our discussions on latches and flip-flops. Uh, we already studied SR latches in the previous set of slides. And then in this one, the new concept was the inclusion of a gate terminal in addition to the set and reset signals, which allowed us to control the overall operation of the latch. And then we also looked at a different version of the latch where instead of using set and reset signals separately, we just used a data signal where essentially, it is set up in a way that set and reset terminals will never get the same value. Like they will never both be one, something like that. And we achieved that by simply incorporating an inverter and feeding the input to the reset, for example. And we looked at how the timing diagram looks like for each one of these latches: SR latch, gated SR latch, and gated D latch. And this is very important to keep them in mind. And I told you, I think that timing diagrams will be crucial. They will be part of your final exam as well. So please make sure to practice the timing diagrams. And I always keep these K maps on the side so that you have this idea as to how that is related to conventional combinational logic design in general. So there is some similarity with combinational logic, except for the fact that there is a history involved. That's all. Okay, so today we'll start looking at the flip-flop again. And I hope by now you understand this. Flip-flops are basically extended version of latches. So you connect two latches back to back and you get a flip-flop. Now, if you connect two SR latches, you get a SR flip-flop. If you connect two D latches, you get D flip-flop and vice versa. And we'll see a few other types of flip-flops today, in addition to SR and D flip-flops, all right? So let's start with the D flip-flop first, where this is the symbol, of course, and we need to get used to the symbols properly, because in most digital systems, when they draw this, they will be using the symbol. They don't go down to the granularity of gates and how things are cross-coupled and whatnot. They typically want to stay within a higher level. So Q and Q bar are the two outputs of the latch, as you know already. For this case, this is the outputs of the flip-flop. And remember, a flip-flop has two latches. Let me just move forward here. So these are the two latches in a flip-flop. Okay, so you have one output, second output, right? You can mention that as Q and Q bar because they're typically always inverted versions of each other. So that's why. And then you have an input D. And for the gate input, remember, we could always call it a gate input, but typically the approach that we use is use the term clock for the gate input, right? Okay, so keep that in mind. So that's why you have this clock input and data input, and you have Q and Q bar as outputs. Okay, and there is a difference between these two symbols, just so you know. When you see this extra circle with the clock signal, that represents that it is a falling edge trigger. This is a standard that we always use. So flip-flops they will be triggered by the edge of the clock, as I keep telling you, right? They are not triggered by the level. Latches are triggered by the level, high or low. But when you connect two latches together, the flip-flops will be driven by the clock edges. Now you can design them in a way that they will be driven by the positive edge or rising edge of the clock, or they could be triggered by the falling edge of the clock. So this symbol is used for the rising edge triggered flip-flop. And when you have a circle with it, it represents falling edge triggered flip-flop. All right. I hope that makes sense. Now, just to quickly take a look at the truth table as well. Remember, for sequential logic, truth tables are, timing diagrams are more crucial than truth tables essentially. But still, just to make sure that we stay in touch with our truth table, I always keep them on the side so that you know. So here is how you can read the truth table. When the data is 0, your output is going to be 0, doesn't matter what it was before. Notice. So even if your output was 0 or 1, now it is going to be 0 because it is driven by the data. Similarly, when the data is 1, your output will be 1, doesn't matter what the output was before. So your output is directly driven by data. And you can say that this is a very simple function to represent. Your output is going to be the input. That is how simple a D flip-flop is. Does that make sense? No complication. Unlike set and reset SR latch, where there are some combinations that led to changes, here, whatever the data is, your output is going to be exactly that. So D flip-flops are typically really nice, almost like a buffer. They provide the input to the output without any changes. But the difference is, unlike a buffer, which will always keep sending the input to the output, flip-flops will keep sending the input to the output in regular intervals. And dictated by what? Dictated by the clock edge. So if you have 10 clock edges, it will let 10 instances of the input to the output. So that's how you synchronize. And that's why it is called synchronous circuit. All right. And by the way, we don't even show the clock signal as any input here. Notice, if you haven't noticed that yet. We don't typically show that as a separate input because the only thing it does, it provides clock edges. And at every edge, every positive or negative edges, you have some changes. And these are the changes you get. So that's why typically in textbooks, they don't show the clocks. Yes. It's a great question. Okay. I'm glad you asked. Did anybody, any of you, I've been telling this for a while that, hey, latches are driven by the clock level. Is it high or low? And flip-flops are driven by the edge. This is a great question. You never asked me, hey, by the way, how does this flip-flop understand where the clock edge is, right? And how is it? I mean, I never explained it deliberately because I wanted to talk about it at some point, but thank you for preempting the question. So can anybody help me answer that? And for that, I will be using this timing diagram. I think this will do. Yes. First of all, that's a good point. So we can use some specific circuits to detect an edge whenever there is a change, rising or falling. It's true. But do you see any kind of circuits connected to the flip-flops? No. Flip-flops are, I mean, you have seen the circuits. There is no extra circuitry used to detect the edges. What you said is right. We can have edge detection circuits for some other specialized purposes, mostly analog. But for this particular flip-flop, we don't have any separate block that is helping you detect the edge. But how does it detect the edge? See, if you don't ask, you'd never know. Thank you. You should thank your colleague. So, all right, let me, for the interest, anybody else want to try? Yes. Absolutely, absolutely. Thank you, thank you, thank you. So he's right. I don't know whether you caught his explanation, so I'm going to repeat that for you. Notice, that's why I have this slide open for you. So you have two latches, right? And remember, you always design them in a way they're exactly opposite. So if one of them is positive, the other one is negative latch. So one of them is triggered by the higher level of clock, the other one is triggered by the lower level of clock. Never the same. If they're the same, then they can never detect the edge. Okay. So notice the way it works is when you have a clock signal like this, say 0, imagine, and this is the first latch is triggered by the lower level of clock. You know why? Because notice when you get 0 here at the clock, you have an inverter, so it becomes 1. So your gate becomes activated. So this latch works. But the other latch gets 0, so it doesn't work. Okay, so your latch essentially sends the data to the output up to this point. So P becomes Q, but nothing happens to the next stage because it is inactive. For the same level of the clock, the second stage is inactive and the first stage is active. But when you go from 0 to 1, notice now this clock is 1. So this input is 0. This input is 0. That means it will stop sending the data to the output. Right? It will stop sending the data to the output. Even if you keep changing the data, doesn't matter. You don't send anything to the output anymore. But meanwhile, let's see what happens to the other guy. So this 1 will be given to the gate input of the second latch. And now it is activated and say, hey, give me some inputs. I'm ready. And it will see the only input that it will see is what was sent before. Right? So it will see whatever was here, which is, again, the data that you sent. And this data will be sent to the out. Yes. That's a great question. But notice, that's a great question. First of all, the difference between an XOR gate, which looks at exclusivity, and this type of approach is that time. So there is a concept of time involved here. Okay. But XOR gates, they look at one instance and decides on the output based on that instance. They don't even care about whether my output was 0 or 1 before. Right. So that is the difference. There is the similarity, and it is coming. I mean, I'm glad that you are trying to connect this, because okay, let me just show you where we are going. Do you see that there is an XOR gate here? So right, it's good when you think about stuff and try to connect them. It's good. So we are getting there, honestly. But so there is some similarity with XOR gate, but it is not essentially an XOR gate. Okay, there are some XOR logic hidden inside the pattern. All right, so notice we design these circuits in a way that they take turns, like a relay race. Only one of them is activated at a time. So what happens exactly at this edge, folks? What happens there? At this point, this latch starts turning off, the other latch starts turning on. Do you guys all agree? Right? At that moment of time, there is a direct link, essentially. So they interact with each other, and then one of them has to stop. Either one of them has to stop, and it cuts off the data. Doesn't matter whether the first one stops or the second one stops. There is no direct link from the data to the output, except for one situation. What is that? This time step. Does that make sense at all? Let me show you one more time. So imagine when the clock goes from high to low, its invert will have to go from low to high. But is anything perfect, folks? Will they be instantaneous? No. Whenever you have an inverter, the output will come after a certain delay, no matter how small the delay, 1 nanosecond, 2 nanosecond, 10 nanosecond, doesn't matter. There will be some, sorry, give me okay, yeah, here. So there will be some delay here. Sorry, I meant to invert it. I didn't. So let me invert it now. So I meant to show you that when it was 1, this will be 0 and then 1. So notice for a portion of time, let me zoom in again here. For a portion, I'm deliberately trying to keep the delay small, but notice for a portion of time, you see that both clocks can be 0 or both clocks can be 1, if I put it in a way. So both of them can be activated for a small period of time, and that period of time is always at the edge, always at the edge. So it could either be both 0 or both 1. Okay? So that's how naturally it detects the edges and responds to the edge, and then it stops. One of them stops, gives up. Right? Okay, thank you for the great question. So notice, you almost didn't even know how these circuits are. I was gonna talk about it, but thank you for asking. All right, so now where were we? We were here. So I fast forwarded to show you how the D flip-flop looks like. So you have latch 1 and latch 2, and they are connected to each other, driven by a clock, and that's how you get the D flip-flop. Okay, and I still want to show you the timing diagram, and please pay attention to this, because you will have to draw a timing diagram, and it is not confusing until you have to draw it yourself, honestly. When you have this on the slide, oh yeah, sure, everything makes sense. But if you don't practice enough, you will see it's not really that easy. So please pay attention as I describe this. So first, let's start with clock, which is, I think, the least confusing signals of all, because it is really nice and repeated. This is our clock signal. Okay, let's start with the clock first. Simple. And now we decide on a data. You could draw any random pattern, or I will give you the pattern. I will give you the data pattern. So without any loss of generality, we decided that our data will be like this. You can change it to anything else you want, toggling between 0 and 1, because it's a digital signal, of course, digital data. All right. The only thing that you have control over is Q. And that's the one we have to track together. Let's see. Okay, and I told you, I gave you a hint that for this example, we're looking at a falling edge triggered flip-flop. I'll have to tell you, otherwise how do you know, right? So we should only look at, notice the one that is marked here, the falling edges right here. falling edges of the clock, all right? So let's see. Interesting. First of all, at the falling edge, the very first falling edge, and don't worry about what was there before. It could be 1, it could be 0, because I have no way of knowing. So initial few, seconds, nanoseconds, we don't know honestly what to do with. So we initialize it with whatever, 0, 1, we don't care. Before the first clock edge appears, right? We don't know. Like, you can start with 0, you can start with 1, I don't care. Okay. But starting from the very first clock edge, this is the first clock edge. At that period of time, the flip-flop looks at the data for the first time, and it sees the data is, folks, 1 or 0. 1 or 0. 1, you can see that, right? Yes, it became 0 shortly after it, but the flip-flop doesn't know. The flip-flop just saw, oh, the data is 1, sure. And it tries to be 1, but does it become 1 right away? No, because of the delay. But that 1 is propagated eventually to the output. So there is a slight delay, little bit of a delay, but after the delay, it becomes 1. Once it becomes 1, notice that the data gradually became 0 eventually, not too long after, right? Very soon. But the output didn't care. You know why? Because the edge is gone. The clock edge is gone. It only looks at the data at the clock edge. Before or after, even if there is a change in the data, it doesn't care. So it will hold on to that value that it saw for a long period. Until when? Until the next falling clock edge. Okay, this is the next falling clock edge. You don't even look at the data. You basically just keep going with whatever you had before. This is the latch action. Remember, I kept telling you, latching meaning holding on to something. So basically, it is holding on to the data. It is latching onto the data. That's what you are seeing here. Until the next evaluation period occurs, which is the next falling edge. So during this falling edge, let's behave like the flip-flop here, okay? It looks at the data again. What do you see? Do you see 0 or 1? At this falling edge, do you see 0 or 1? 0. So you will try to be 0. The output will try to be 0, but you don't get to 0 right away. There is a delay, of course, but after the delay, you become 0. And then you stop paying attention to the data altogether. You don't care. Until when? Until the next falling edge, which is right here. And you look at the data at this falling edge and you see the data is 1. And then you try to become 1 with a delay and so on. Does that make sense to you? Okay, so for the interest of time, I will not repeat it too many times because I have other timing diagrams coming up. We'll have plenty of practice, but please practice at home. And I recommend try to draw it yourself. Like start with D and clock, and then don't look at Q. Try to draw Q by yourself and see whether it matches with the one that is here. Okay, now this is something that we have already covered because I fast forwarded, but I want to also show you the rising edge triggered version of the timing diagram so that we have an extra practice. So let's do it one more time. Ready? I want to show you that. So this is the clock signal that you see, but internally there are actually two versions of the clock, one being fed to this latch, the other one being fed to that other latch. And that's why there is a slight, overlap. Do you see that? There is, I don't know if it is visible. If you follow the edge between G2 and G1, G2 is basically the second node, G1 is the first node. Okay, so can anybody tell me why G1 is lagging behind G2? Can anybody tell me? This is G1, by the way. Why is it lagging behind G2? Thank you, inverter. So G2 is directly driven by the clock, but G1 has an inverter in between. So any logic gate will add a delay. And that is deliberate, of course. And that's why you somehow create an edge effect, okay? At every point where the clock changes. Okay, now you don't necessarily need to show both, actually. Even in your exams, I might just show you the clock, that's all. You don't need to look at G1 and G2 individually, just follow the clock because you know what it should do. I already told you that it is a rising edge triggered flip-flop. So just look at the clock signal. So to look at the clock signal, should I look at G1 or G2, folks? Tell me. G2. So I can get rid of G1 if I want to. This is just for your information, all right? I can just give you this clock signal, done. I will not give you G2 and G1 both, all right? Just clock signal. And then this is something that you have full control over, or I have full control over. I will draw a random data stream, whatever, I don't care. I'll give you random digital data, zeros and ones, zeros and ones. And then you have control over two things, P and Q. Essentially, let's not even worry about P, because if you look at the black box and look at the flip-flop, you get the Q eventually at the output, right? So let's take a look at the Q. Since it is rising edge, so let me just get rid of the signals that you will probably not need. These are for your information only. So let me get rid of these signals. You need clock, you need data, and you need to get the output. So let's try to find the output now. First, since it is rising edge triggered, you see the rising edge first. At this point, was the data 0 or 1? 1. So your output will try to become 1 with a delay. I know it's a little bit on the lower side, but let me try to put it here. Okay, so it will try to become 1 with a delay. After it becomes 1, it will no longer care what happens to the data until the next rising edge, until you get to this point. At this point only, it looks at the data and it sees that the data is 0 now. So it will start getting down to 0, which is here with a delay. So you see, your output is not responding to all the changes of the data. It is only responding to certain changes that you are synchronizing with the clock edges. Does that make sense? I hope, as you see, as you go to the higher level and don't worry about the cross coupling, blah, 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 things become easier to handle, right? So that is the beauty of digital logic design, because there are hierarchy. You go down to like lower level circuit connections to a little bit higher level symbols, to even higher level where you deal with blocks, like, okay, like registers instead of flip-flops. You know, if you have like multiple flip-flops connected together, that's a register, as I told you. We basically deal with a very higher level in regular life. When you're dealing with an FPGA, when you're dealing with a processor, you don't have to go down to this level of granularity if you don't enjoy that. Okay, now this is a repeat of what we have kind of discussed, but in a different light. Let me show you. We already discussed SR latches, didn't we? So this slide will show you SR flip-flop without any, you know, I think it's pretty much standard. We studied about D latches and then D flip-flop. Now we are looking at SR flip-flop. So this is an SR latch. I hope you remember that. This is another SR latch. Okay. And the very first slide of this lecture showed you that this is a gated SR latch because this is a gate signal. Remember that, folks? This is a gated SR latch. Okay. Now, this gate is basically driven by the clock signal essentially. So wherever there is a gate, just drive it with a clock. So you have this clock and clock inverse being fed to two stages of the latch. This is the first stage. This is the second stage. All right. So historically in textbooks, people used to use the term master slave flip-flop, but now they're changing the term, of course. But as of now, the textbooks still use this, and most data sheets in industry will use these terminologies. So apparently, let's see how the output should behave for an SR flip-flop. It is not as easy as the D flip-flop, because in a D flip-flop, you just have the data and the output done. But here you have set and reset signal. If there are multiple signals, as you see, but please pay attention as I draw, and I hope things will make sense. Let's do it together. So I'll start with the clock. Okay, so this is your clock, which you can decide on, like time period and everything. Clock bar is basically generated by the clock with a delay, small delay. So these two rows are done. Now set and reset are the two signals that you have control over. You decide when to set, you decide when to reset. It is not like data, by the way. There are two signals that are independently controlled, but there is a catch. Can anybody take a look at these two rows and tell me a combination that is missing? By combination, I mean 0, 0, 0, 1, 1, 0, 1, 1, right? For between set and reset, just look at the timing diagram here. So this is 1, this is 0. This is 1, this is 0. This is 0, this is 1. This is 1, this is 0. This is 0, this is 1. Which combination don't you see? Thank you. 1, 1, 1, 1. Why? Do you remember now? Because in the latch discussion, we already discussed, you cannot allow set and reset to be both 1 simultaneously. That will lead to, even 0, 0 is fine, but 1, 1, no. That's why. How do you ensure that? We saw an example by adding an inverter and whatnot, but somehow you have to ensure it. And that's why the timing diagrams are like this. Okay. Now, let's follow along and let's see what P and Q should do. Let me show you. So let's just move directly to, you know, P and Q. So let's follow S, set and reset. Set and reset are these two signals. Okay, the very first set and reset. You don't have any control over the internal set and reset because they are directly driven by the previous stage. Okay, you have control over the very first set and reset. Okay, notice. Remember, this is no longer a latch. Simply, notice one thing. This set is 1. Set is 1. Your output is 0. Hold on a second. With set, don't you think the output should, like, set should set the output to 1, right? That's what we have in mind. But don't forget, this is not a latch. This is a flip-flop. It is not driven by the level. It is driven by the edge. So which edge should we look at? I mean, I have to tell you, but essentially for this one, it is a rising edge, figured. Okay. And let's see. So this is the rising edge of the clock. And at this edge, it will look at the set and reset. And at this edge, it will look at the set and it will see the set is 1 and reset is 0. So it will try to set the output to 1. And that's why the output is going to 1. If anything, honestly, drawing the timing diagram for flip-flop is much easier than a latch because you just have to look at the edges and don't do anything in between, right? For latches, you have to keep following every level, 0 and 1, every level, do something between every level. Okay, so now after that, it stops following altogether. It doesn't care what goes on with reset or set, reset or set. We don't care. We move forward and go all the way up to the next rising edge. So this is the first rising edge. This is the second rising edge. At this edge, let's see, at this edge, it looks at set and reset. Now set is 0, reset is 1. So you have to set the output to 0. Does that make sense? Reset 1 indicates you have to reset the output. So your output has to be 0 now. So it starts going to 0 with a delay, of course. And then it doesn't care about set and reset anymore. It completely ignores it. Next, at the next rising edge, it looks at the set and reset again. Now set is 0, reset is 0, right? Do you see my point here? Let me see. Does that make sense, folks? Okay. So at every clock edge, you look at the data and you change your state accordingly. All right. I will show you an interesting version of this SR flip-flop in this slide. And we are basically, I kind of skipped something, which I didn't tell you, but here I will discuss this. Okay. I skipped a feature that we already, kind of noticed. So JK flip-flop. JK flip-flop is a version of an SR flip-flop. Okay. And here is how it works. Basically, J and K are similar to set and reset signals. J is treated like set, K is treated like reset. Okay, when J is 1, you try to set the output. When K is 1, you try to reset the output, and so on. Okay, there is one extra feature in JK flip-flop. That is, this flip-flop allows you to use the combination 1, 1, meaning both J and K can be 1 simultaneously. Unlike in SR flip-flop, where you cannot have S and R both be 1 simultaneously. Okay, and let me show you what changed here. Just take a closer look. Now, I hope by now you are behaving like digital engineers, digital circuit designers, just take a look at this circuit and tell me the type of changes you see. There's some logic output, and obviously we are not going to start from the very root level for every circuit here because we have to cover a lot of ground. We started, remember, with cross-coupled NOR gate, and then showed you how latches work, eventually moved to cross-coupled NAND gate and showed you that this is also a possibility, and so on, right? Imagine something like that, but with a twist. What are the changes do you see between this circuit and an SR, conventional SR flip-flop or SR latch? If you want, you can just focus on one of the latches, if you want. What are the changes you see? It is, thank you. That's one. Instead of NAND logic, we are using an AND logic here. This is good. Yeah, by making some changes, like I said, by making some, okay, somebody comes up with the concept of latch. Okay, that's how the scientific process works. You don't just jump into a JK flip-flop all on a sudden. Hey, JK flip-flop, done. No, you think, like I said, you invent the phenomena of a latch circuit that holds on to the output, that can remember its output and not change it unless you do certain things. This is an interesting phenomena. Somebody invented it. And somebody else came up with this idea. Hey, hold on. I could use two of these circuits and do something crazy, create a circuit that will only respond to the edges without using a separate edge detection circuit, which is often complicated, right? You can use op amps and others to detect edges, by the way. So that there will be huge circuits. As opposed to that, a simple digital circuit can detect edge because you have two types of latches. Okay, fine. And somebody says, hey, hold on. In your flip-flop, you cannot have these two signals one simultaneously. What if accidentally you end up with that and then you have garbage output? How can you handle this? So somebody modifies this design. Okay, if you do so and so, so and so, you can now use both signal to be one if you want to. Does that make sense? You see my progress here? So it's not like, hey, all on a sudden, we wake up and we see that, hey, this is how you design JK flip-flop. There are logics and many months or years of efforts and thinking that went behind discovery and invention of these designs. We are just getting it from slide to slide, that's all. But they didn't appear, overnight, of course. So my point is, through intensive reasoning and studies, people figured out that with this modification, if you change this NAND gate to an AND gate, and also there is an extra input, notice, in typical SR flip-flop, let me move back to the previous one, you have S and R signal, and you have one gate signal. So this were what? Two input AND gates, all right? But here, this is three input. So 1, 2, you have the gate signal as well, but you have an extra input coming from somewhere. I'll show you where it is coming from. But there is an extra input, an extra feedback. It is coming from the second stage. Notice the second stage. And deliberately, I'm not getting into the detail of the logic here, but apparently by making this modification, which is not too much, honestly, you still have the same design, except for the fact that you add extra feedback. That's all. This AND gate was already there in the gated latch. If you don't remember, let me just move forward to the very first slide. We started using this gated latch with set and reset, and you can also redesign it with AND gate if you want to. At some point, we moved to AND gate for D latch already. Doesn't matter. You can design any logic with, say, NAND gate or NOR gate or AND gate if you want. And then eventually here, we saw an SR flip-flop with AND gate because we were building towards it with AND gate. You didn't notice that. You didn't notice the subtle changes because I didn't point it out. But now I am pointing it out that you can design this with AND gate, and that allows you to incorporate this logic of a JK flip-flop. Yes.
So you still use the same terms for the two flip-flops if now the second one is affecting the first?
It's a great question. No, you cannot. You have to update your truth table and everything. So we are going to do that. Yeah. So basically, by adding an extra feedback, you change the dynamics. It's no longer as simple as an SR flip-flop. For example, there are additional features. So for example, now you can use this one-on combination. But how are you going to use it? What will be the logic? That entire logic will change. So your it looks like, what I'm trying to tell you is it looks like an SR flip-flop. There is some similarity because J is like S, K is like R. But when J and K are both are one, what does that mean? Are you trying to set or reset, or how do you set and reset simultaneously? What do you do? Just think about the logical conclusion here, right? I ask you to set, you set the output to 1. I ask you to reset, you set the output to 0. But I ask you to set and reset, what do you do? In terms of logic, what will you do? You don't know. You see them? See my point here? We'll figure it out right here in this slide together. So, but do you see the changes here? And if I ask you somehow, I don't think I will ask you to do so. I might give you a half-baked version of a circuit and ask you to modify it into a JK flip-flop. So it is important for you to pay attention to what changed. Or I can show you 2 circuits and ask you which one is JK flip-flop. You know, a JK flip-flop has a feedback from the final stage output all the way to the first input, not an SR flip-flop. So even if you don't have to memorize the entire circuit and like, it's not about drawing essentially, it is about learning the changes. Okay, so keep that in mind. Now, I'm getting there. I'm getting to what happens when you have both cases 1. Let's start with this. So imagine when your J and K are both 1. This is the combination that we care about. You know what? Let me start with something simpler first. And let me not just jump into the most difficult part here. So when J is 1, I told you it is like set, didn't I? So it is setting the output to 1. Even if your this is your previous output, remember. If your previous output was 0, you make it 1. If it was 1, you still make it 1. Basically, it is the set that is in control. Okay? All right. Now, when the reset is 1, which is basically K here. K is the reset. I told you, right? Then you make your output 0. You don't care what the J was. You don't care what the previous output was. Say, when you see K is 1, you make it 0. Make the output 0. Given that J is not interfering with K, J is deactivated, but K is 1, so you reset the output. Does that make sense? So these combinations show when J and K don't fight with each other. One of them is 0. When both of these are 0, you're not trying to set or you're not trying to reset. What do you do? What did we do for SR latch, folks? When set and reset were both 0, what did we do? We didn't change the output. The output remained as was. So basically, if your output was 0, keep it 0. If your output was 1, keep it 1. So up to this point, you see, in terms of just pure Boolean logic, nothing changed. Do you guys all agree with it? Okay, now let's see what changed here. When both of these are 1, here's an interesting part. If the output was 0, make it 1. If the output was 1, make it 0. This is called toggling. Okay, basically just toggle the output. Whatever it was, just change it. That's all. That is the logic, extra logic. Okay, and by the way, using that's why I told you the story behind it. I mean, you might be wondering, why would you do that? Why? This is a feature that you get by going through this approach. At least now when you have both set and reset 1, you don't have like your system frozen, like, hey, I don't know what to do, right? Your system does something and you can predict what it is going to do. It will toggle. If you know it is going to toggle, you can always toggle back, right? If you want to, you can always toggle back. So it is controllable now. It is not a situation where your system will be stuck, first of all. Second, people are never satisfied with just, okay, this is another feature, fine, it's just there. If there is a feature, they will use it. Okay, so by the way, see, T flip-flop, somebody came up with an idea to use this feature particularly to make a certain flip-flop known as toggle flip-flop, which specifically uses this toggling feature of JK flip-flop. You see, that's how engineering is. Somebody does something and others come up with ways to make better use of it. But do you see the progress from SR to JK, folks? Does that make sense to all of you? All right. I'm going to show you the timing diagram one more time because that is the king here. Timing diagram is the king. Let's see. This is your clock signal, which you have no problem with. It will be given or you can draw it. It is a nice uniform signal. J and K, I would like to point out something interesting here. These are like S and R, right? But except there is a twist. Do you see this region? What is J? 1. What is K? 1. So for the first time ever, as opposed to a SR flip-flop, we're looking at J and K both being 1. So we'll look at this option, okay? So now let's start with this. When J is 1, and by the way, without any loss of generality, we are treating it as a rising edge triggered flip-flop. You can always do the opposite. You can always do the falling edge triggered, okay? Are you still with me? So when I provide a question for your exam, if you see an arrow pointed to, this is also an approach that people often use. The arrow pointed to the rising edge, you understand that this is a rising edge triggered flip-flop. Or if you see an arrow connected to the falling edge, you understand that this is a, so basically we indicate which edge you should respond to with an arrow sometimes. Or sometimes they do this, show the edge. Sometimes they just mention it is a positive edge triggered flip-flop. So there will be one way or the other, which edge to follow. Okay. So for us, we'll be following the rising edge. And remember, without the edge, you don't even care whatever the J and K is. You don't care about any other values, only at the edges. So let's see. At the edge, your J signal is 1 and K is 0. J is like set. So what do you do to the output, folks? You set to 1. Still with me? Okay. Now, and then you stop because you don't care about anything else until the next clock edge appears. Okay, so this is when the next clock edge appears. And you look at J and K again. Now J is 0, K is 1, as if you're trying to reset. So you reset the output down to 0 after a delay. Okay, now you look at the next clock edge here, where you see both J and K are 1 now. This is new. This is just running around in different places. So 1 and 1. Okay. So now both J and K are 1. That's new for you, but you know what to do. You toggle. So you look at what your output was. Previously, my output was 0. So I'll just make it 1. Not because set is telling me to make it 1. Because reset is also telling you to make it, 0. But you just toggle. Whatever your output was, just change it to 1. If your output was 1, you would change it to 0. Does that make sense? This is just simple toggling. What if your set and reset continue being 1 and you have another clock edge here? You toggle again. At this point, you toggle again. That's all. You just keep toggling. As long as the set and reset are both 1. This is a special mode that you get. Now, question is, you just get it. JK flip-flop doesn't get stuck with J and K both being 1. It gives you a toggling feature. Can you do something with it? I don't know. We'll figure it out. So some engineers figured out what can you do with it. And that is T flip-flop. Let's see. Are you still with me? And get used to the symbols, by the way. When you see a symbol of a flip-flop like this with T mentioned here, you understand this is a T flip-flop or toggle flip-flop. And what it does is it basically okay, so this is the slide. Sorry, there was an animation issue. This is the right one. Okay. So essentially, look at how you can create this T flip-flop using a JK flip-flop. Notice, I'm going to show you here. Do you see the change here? Can anybody tell me what's going on here? You make J and K connected as one common input and provide that input as a toggle signal. Folks, still with me? When the toggle is 1, this is essentially JK flip-flop, guys. JK flip-flop. And it will keep toggling the output when the clock is, right edge. At every edge of the clock, it will toggle the output. So it will be like a clock again. Okay, let me ask you one thing. If the toggle is 1 and you provide a clock, what will the output do? At every positive or negative edge of the clock, it will keep changing from 0 to 1, 0 to 1. It will be like a clock itself. It will more like mimic the clock almost. Do you agree? Okay. All right. But what if my toggle signal is 0? Then what? Then you get both J equals 0 and K equals 0. Do you guys remember what happened when both set and reset were set to 0? You should remember. What does the output do? Latch. The output doesn't change. it will basically hold on to itself. So similarly, when J and K are both 0, nothing happens. The output remains, as it was. Okay, so let's see from the truth table first. This is your toggle signal. You don't need J and K separately because you have connected them to one input. When the toggle is 0, your output remains as it was. See? But when the toggle is 1, your output changes. If it were 0, it becomes 1. If it were 1, it becomes 0. So it toggles, keeps changing. Simple, super simple. And this is often used to design counters, basically, okay? Counters. We haven't seen where these components are used yet. That's more like the next level. When you take the next course, 300, I forgot the number, 3 something, where you do this digital system design, you use these building blocks like flip-flops, counters, blah, 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 to make something, right? And then you understand, oh, wow, we are using a D flip-flop. You are using a T flip-flop. We are using so and so, timing IC. So you use different components as building blocks to a bigger digital systems. Okay? So for now, you're getting features. You're getting used to these features. All right, one more thing, if you haven't noticed, and these are all long discussions in the textbook, but you see how easy it is to relate to? This is a truth table. If you haven't noticed, 00011011 and all the output you get, this is essentially an XOR gate. If you see the, the combinations, it's an XOR gate. So we can always represent a toggle flip-flop as an XOR between the toggle input and the output. If the toggle input matches the output, then do something. If they, you get my point here, right? So essentially, you could represent. This is a really nice coincidence per se, I would say. And based on that, there is this extra diagram I have on the side, which I want to also point to. So this is a JK flip-flop that you converted to toggle. But you can always use a D flip-flop as well. You can always use a D flip-flop and convert it to a toggle signal. Here is how. Notice. Are you still with me? What does a D flip-flop do, folks? It just takes the data and sends it to the output. No other complications. Take the data, send it to the output at the appropriate clock edge. So you just have to make sure your data is like the toggle function. What is the toggle function? The toggle function is toggle signal XOR output. This is the toggle function. Am I making any sense here, folks? This is the toggle function, okay? So what you do is you take the toggle signal, you take the output. So what you get here, you get toggle XOR output. Does that make sense? You make it the data. That's your data. That the functional output is your data. And now you have the D flip-flop, which is basically gonna send the input to the output. So you can always make this is just a fun example, right? You don't have to do it. You can always use the JK flip-flop to make a toggle flip-flop because that's how it basically came into being, honestly. But you can always use, and oftentimes I remember when I was working on some projects as a student, we had D flip-flops in hand. I don't have a toggle flip-flop. Sure, I can make the D flip-flop a toggle flip-flop. See my point here? By programming it appropriately, especially if you have a board like basis 3, you can always make logic as the way you want, right? You can code it in. So you don't need a separate, you need to buy a T flip-flop and JK flip-flop and SR flip-flop to do some project. You can convert one to the other. And that was an interesting exercise as well for us. Convert this flip-flop into that other flip-flop. Sure, here is how you modify it. Okay, all right. And in terms of timing diagram, let me finish with that. We just have 1 minute, which is fine. So you have this clock signal. Let me show you the toggle signal. When toggle is 0, notice, this is your output. This is the first clock edge. What was, folks, we don't see the data anymore. We see that output. Your output was what? Please respond quickly. 0. So it remains 0. Okay? It just looks at itself, the output. Okay, next. This is the next clock edge. Now the toggle is 1. So the output looks at itself. I was 0 before. I should toggle now because toggle is telling me. So it toggles to 1. Next, this is the next clock edge. What is toggle? Toggle is 0. So it will not toggle anymore. It will remain what it was. So now it was 1, it remains 1. Next clock edge, now toggle is 1, so it should toggle. It says I was 1, now I'm going to be 0. So it just looks at toggle, whether toggle wants me to toggle or not, and then looks at itself. What was I? I was 0. Should I toggle? Sure. Right? You see my point? This is an interesting feature. It just looks at the output itself and decides on the next output accordingly. Okay. So, all right. So that's where we stop today with T flip-flop. We'll start with timing matrix in the next class. Have a great weekend. Thank you.